Hello everyone. Today we'll be covering CIE AS enthalpy changes of CIE A-Level Chemistry. I'll split this video into three parts, and today we'll just be doing part one, or whenever you're viewing this video. In today's part, we'll be covering the definition of heat content, the important enthalpy change graphs plus the effects of catalysts on the graph, and the definitions of enthalpy changes in essence formation and combustion. I'll cover the rest of the definitions in a separate video, which is basically part two. And the last thing that we'll be doing today is an introduction to Hess's law and the formation and combustion cycles with example questions. So let's begin. Unlike your IGCSE years, where enthalpy changes was rather simple and just involved bond energies breaking and forming, in the A-level section, enthalpy changes becomes a bit more complex, and it involves other enthalpy changes such as combustion, formation, neutralization, hydration. And in your A2 part, we talk more about hydration, neutralization, solution, and also lattice energy and electron affinities. Now, I don't mean to scare you or anything, but it's really simple once you understand the concept. Anyway, let's begin. So the first thing that isn't really important, like not too important, I don't see it mentioned in your syllabus, but it has come as a past paper question. I don't remember when, but it has come, and that is the definition of heat content. Now you do not have to know very much in depth of what heat content is, but the definition of heat content is basically the percentage, no, sorry, the heat content of a body is the percentage of energy in the body which can be converted to heat energy. Okay, this is just a definition, and this is all you really have to know. This is the only thing that I've seen that's been asked. And what do you mean by this? Like, what is the percentage of energy in the body which can be converted to heat energy? Well, for this you need to know the important principle of conservation of energy, and that energy is neither created nor destroyed. It is just simply converted from one form to another. So let's say you eat some food, all right, and you eat 300 calories of energy. Okay, 300 calories of energy. And out of this 300 calories, let's say 150 calories is being put to useful work, mechanical work, such as moving your arms or just any or every metabolic or cellular activity, whereas 150 calories is gone to heat energy. So for this food that you just ate, which let's call this X, for X, the heat content is 50% or 1/2, because half of this can be converted to heat energy. I hope that makes sense. So that is it for heat content. Let's move on to the more important things. So a lot of enthalpy changes, like the ones that you're familiar with, are things I won't stick too long, like dig too deep into. But one of those things is the enthalpy change graphs. Okay, and there's two graphs essentially. One is for exothermic reactions, and one is for endothermic reactions. And these graphs are important, so you have to like be able to identify and draw them if required. So for exothermic reactions, as most of you are aware, energy is given out. Oh yeah, and this is what on the left hand, on the y-axis, I believe, is the energy, right? Energy, and on the x-axis is, well, just with time. So the reactions progress with time. Same here, time. Right. So for exothermic reactions, you know that energy is released, energy is given out. So that means from the reactants, the certain amount of energy is required, which is known as the activation energy. And then in the last stage, the products are at a lower energy level than the reactants. In this way, you see that the energy of products and reactants are different, where the energy of products is lower than the reactants. So where is that excess energy going? So it's released. So that is why it's an exothermic reaction. Energy released. This is the energy that's released. So when you're asked to label such a graph, you should also know how to label it. So to label it, this is the enthalpy change of reaction. This is the difference between the energy levels of the reactants and the products, whereas this is the activation energy. Okay. Now for endothermic reactions, the opposite is true. Energy is taken in to complete the reaction, so which basically means that the products are at a higher energy level than the reactants, right? And this is the activation energy. The rest is just the activation energy. Okay. So in this case, the activation energy would be much larger because that much energy would be required to start the reaction. And in this case, this is the enthalpy change, right? In this case, it's endothermic reaction because energy is taken in and the products are at a higher energy level than the reactants. I hope that makes sense. Now, what is the effects of a catalyst on this graph? So let's say if this is a graph, okay, and this is another graph. So this is for endo, and this is exo. So what would happen, like how would this graph turn out if I were to add a catalyst? Well, if I were to add a catalyst, the activation energy would lower, right? But the enthalpy change would remain the same. So no matter what happens, no matter what catalyst you add, the enthalpy change of a particular reaction will be the same. So for this reaction, it'll be something like this. So the activation energy is barely lower, right? It should actually end and like start and end at the same point, like the reaction, I mean. So it should be like this. So it should end properly there. Pardon the graph, it's not very accurate. And for this, it should be like this, right? It should end and begin at the same point. Or it can also be like this. Just follows the graph along. So the activation energy in this case is much lower, yeah. And the activation energy in this case is also much lower than the original activation energy. Catalyst. So that's what would happen if a catalyst was involved in the reaction. Okay, I hope that makes sense. Let's continue. So those are the important graphs that you have to know for this enthalpy changes lesson. So next we'll move on to the most important thing in this lesson really, and that is Hess's law plus formation and combustion, right? So Hess's law, and well, the Hess's law introduces a couple of cycles to us that we have to know for your AS level syllabus. What the Hess's law states is that you don't really have to know the definition of this, but it is provided. So I haven't seen it being asked, but I suppose it's better you know it. So what the Hess's law is states that enthalpy change, I'll just write the symbol, is independent of path taken as long as final and initial conditions are the same. Now this is a bit wordy and perhaps it might not make sense to everyone for the first time seeing it. So let's say, okay, I'll just elaborate on this law with a simple example. Let's say x plus y gives you xy, right? No, sorry, let's do another thing. X plus y plus z gives you, no wait, x plus y z will give you x, y, z, and x plus y plus z will also give you x, y, z, right? So for this reaction, no matter how you start, your end product will be the same, and as long as your final conditions and final initial conditions are the same, you can perform calculations within this cycle and treat it as an isolated or closed system. So you would be able to calculate the enthalpy change that would be required for moving from this to this, or from this to this, or from this to this, or anyway in the cycle. So you can treat this cycle as an independent closed system. And that is where this is how you perform calculations based off of the enthalpy changes of formation and enthalpy changes of combustion. Now, before we move on to the main part, which is standard enthalpy changes of combustion and formation, I'd like to familiarize all of you with the notations that will be used throughout your CAIE A-Level Chemistry. So all of you must be familiar with delta, which is basically change in chemistry. And whenever you see a delta H, that means enthalpy change. Now in your A-Level Chemistry, you will also see something new, which is delta H, or with that, this thing on top of the H. Now what does that mean? Whenever you see that, it basically means that everything is taking place under standard conditions. And elements, or the compounds, in their standard states. Now, what exactly is the standard conditions and standard states? It's probably something new to you, so you don't know what it is. Well, what standard conditions are is basically 1 atm pressure, 1 mole per dm cubed concentration of solutions, and a specified temperature, usually between 0 degrees Celsius to 25 degrees Celsius. For your CAIE A-Level Chemistry, you use 0 degrees Celsius for gases and 25 degrees Celsius for electrochemistry. So let's just use the 25 degrees Celsius or 298 kelvins for this example, okay? So that's basically what standard conditions are: a specific temperature, 1 atm pressure, and 1 mole per dm cube concentration of solutions. Now, what do you mean by elements and compounds in their standard states? Now, by elements or compounds being in their standard states, I mean that the states they would be in at that specified standard conditions. So for instance, in some of the reactions, for example, when you react to water with, with Mg, right? Mg plus H2O would give you MgOH2 plus H2, right? And this reaction is taking place with their elements or compounds in their standard states, where Mg is a solid, H2 is a liquid, and this would also be a solid, or it could be aqueous depending on how much water is added, and this is a gas, right? But when you react Mg with steam, you get another compound, which is MgO, right, plus H2. And in this case, although Mg is S, H2O is not liquid, it's actually gas because it's in form of steam to produce MgO, right? And in this case, if I were to take standard conditions as 25 degrees Celsius, water would not be in its standard state, right? It would not be in the standard state. Why is that? And that's because at 25 degrees Celsius, we know that the melting point of water is, the melting point of ice is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. So at 25 degrees Celsius, water should be a liquid, not a gas, right? So by standard states, I mean that the state at which the element or compound is supposed to be in that specified standard conditions. I hope that makes sense. So that's basically what this symbol means. There's so much just for one symbol. Anyway, so that standard, right? And whenever you're asked to define something which has a standard written in it, right? Standard, like standard enthalpy change of formation, or standard enthalpy change of this, standard enthalpy change of that, you have to mention that it is taking place under standard conditions, or you have to mention that the elements and their elements or compounds involved in the reaction are in their standard states. It's better to mention both, but I see that most of the time, as long as you say that they're in the standard states, it is acceptable. But again, it's better to mention both, okay? And along with this, the standard enthalpy change, right? You can also sometimes see an F, which is for formation, or you may see a C, which is for combustion. Sol is for solution, and if I recall correctly, hide is for hydration, right? And so on. But anyway, we'll worry about those later. But we'll worry about the first two that I mentioned right now, okay? So, the first important standard enthalpy change that we'll be focusing on, and that follows the Hess's law, is standard, or not, let's not say standard now, let's say enthalpy change of formation. Okay. For enthalpy change of formation, the symbol is delta H, which is the enthalpy change, F. And if it's standard, you just have to add that, okay, on top of the H. Now, whatever in this, what from this point on, whatever I do in black ink is normal, and whatever I do in green ink is in standard conditions, okay, when standard conditions are followed. So the definition of enthalpy change of formation is enthalpy change when 1 mole of a compound is formed from its elements. This last part and this part, 1 mole of a compound is formed, and the last part from its elements is very important. So let's say if I were to say again Mg reacting with water, right, to give MgOH2, right? Okay, no, MgOH2 plus. Okay, no, that's not a proper example. Let's just take another example. Na plus Cl2 gives NaCl, right? 2Na and 2, balancing it out. Would this be an example of standard enthalpy change of formation, or a reaction illustrating the standard enthalpy change of formation? The answer is wrong. It wouldn't be. Why? Because in enthalpy change of formation, you see that 1 mole of a compound is being formed. 1 mole of a compound. Is this 1 mole? No, it is not. It's 2 moles. So how would you write this in the correct form? Instead of writing 2NaCl, you would say NaCl is formed by Na plus Cl2, and it doesn't restrict the moles of the reactants that's being used, but it must be formed from its elements. So elements being Na and Cl2. Is Na an element? Yes. Is Cl2 an element? Well, technically it's not. It's a molecule, but it is the simplest form in which chlorine exists, right? So this is an acceptable compound. An acceptable example of enthalpy change of formation. 1 mole of a compound is formed from its elements. Yeah. Let's take another example. Examples are pretty few for this, but anyway, let's just take another example. All right. So we have. Okay. So we have CH2. No, wait. Let me just write it in black ink. CH2 plus H2 gives C2H6. Now, is this an example of standard enthalpy change of formation? The answer is no, it's not, because they're not in their simplest states. Sorry, not simplest states, they're not in their form of elements. Hydrogen is an element. We can consider it as an element because that is the simplest state, that is a simplest form that it can exist in nature. But is this the simplest form in which this can exist? The answer is wrong. So you have to write it in form of its elements. So C2H6 would be formed by 2C, right? 2C plus 3H2. This would be an appropriate example. Okay, I hope that makes sense. So let's move back to our definition. So remember when I said that green ink would be used to represent if it's in standard conditions? So in case this was in standard conditions, you would say that, sorry, you wouldn't write anything here. Enthalpy change of 1 mole of a compound is formed from its elements in their standard states under standard conditions. Okay, that's all you have to add in case you have to mention standard enthalpy change, or if in the question it's written that standard enthalpy change of formation rather than just simply enthalpy change of formation. So you have to be wary of this sign. It's very important. Okay. Now, how would you represent? So this last part where I said that this is not an appropriate example, but this is. How would you represent this in a Hess cycle? Well, you see that even though CH2 plus H2 gives C2H6 is not an appropriate example of standard enthalpy change of formation, it is a right equation, right? So this can, instead of having instead of being an example of standard enthalpy change of formation, it can be an example of standard enthalpy change of reactants, or the standard enthalpy change of the reaction, because you can do, like, if you recall from your IGCSE years correctly, you can do the standard enthalpy change is equal to the enthalpy change of products, no wait, the reactants minus enthalpy change of the products, right? So whatever's on this side, bonds broken minus bonds formed, will give you the enthalpy change, right? So this is an appropriate example of standard enthalpy change of reaction. Now, how do you implement this, like this standard enthalpy change of formation, into this standard enthalpy change of reaction? Well, you see that either ways, 2C plus 3H2 can lead to this, or it can lead to this. That is where Hess's cycle comes into play. So CH2 plus H2 gives C2H6, right? And remember that I said that as long as your initial and final conditions are the same, you can treat it as an isolated closed system. And this is how you would be able to calculate, like, for instance, the standard enthalpy change of formation, or you could even calculate the standard enthalpy change of formation of this, or oh, one important thing that I forgot to mention: elements alone do not have standard and enthalpy change of formation. So in this case, you see that this is a compound, right? So this would have, this is also a compound, so this would have, but hydrogen alone is not a compound, so this would not have a standard enthalpy change of formation. So normally, this is how I write it. I prefer writing it this way. You don't have to necessarily follow it. So in case I was doing something in a very general format, I would say that the formation cycle follows this trend. Reactants of a particular reaction lead to the products, right? And the elements in their standard states. And this leads to this, and this finally leads to this. And this I write as H2, this I write as H1, and this I write as delta HR. And this is the enthalpy change of reaction. This is H2 and this is H1. So by following the cycle and familiarity with vectors, you know that H2 is equal to H1 plus HR. Either ways, your final product is the same and the conditions are the same, so the enthalpy change of reaction from this to from the elements to the products directly should be equal to the enthalpy change of reaction of H1 and HR together. I hope that makes sense. That is what that is how the Hess's law comes into play here. So for the above example, this one, right? You could write the formation cycle similarly. 2 plus H2 gives you C2H6, right? And 2C plus 3H2. H2, H1, delta HR. So from here you can easily perform calculations. So H2 is equal to H1 plus HR. In case you're asked to find out what is the enthalpy change of reaction, you could make HR the subject. So H2 minus H1. In case you're asked to find out what is the enthalpy change of formation of this, you can just like expand the brackets and make that X and solve for it. We'll do examples so you'll hopefully understand what it is sooner or later. Okay. Now let's move on to the next important thing, which is the combustion, which is denoted as delta HC, right? And the definition is pretty similar, but there's a slight change. So the definition is enthalpy change when 1 mole of a compound or substance undergoes complete oxidation, right? Undergoes complete oxidation, in brackets you can write in excess oxygen. Yeah, so that is what the enthalpy change of combustion is. And in case it's in standards, you can write that standard conditions, standard states of elements. No, it's just standard states, not of elements, just standard states. Okay. And when you involve enthalpy change of combustion, you see that it takes place in excess oxygen. So this automatically rules out the enthalpy change of combustion due to oxygen. Oxygen cannot burn itself, and therefore there is no, like, O2 does not have an enthalpy change of combustion. The perfect examples of these enthalpy change of combustions are organic compounds. So let's say we have alkane, right? Wait, let me just erase that. Plus O2 would give you CO2 plus H2O. Now balancing that out, there's there's two carbons, and there's 6, so 3, so 2 into 2, 4, 7, 7 divided by 2, that's 3.5, right? So this is a perfect example of a standard enthalpy change of combustion. Not standard, sorry, just enthalpy change of combustion. Why? Because it follows the definition given. When 1 mole of a substance or compound, so 1 mole of a substance or compound undergoes complete oxidation, and in case hydrocarbons undergo complete oxidation, they give off carbon dioxide and water. So it satisfies this condition, right? And yeah, that's pretty much it. That's all there is for enthalpy change of combustion. Now, also, it's like just like the enthalpy change of formation, enthalpy change of combustions also can be treated by Hess's law and follow a similar cycle, which I like to call the combustion cycle. And unlike the formation cycle, the combustion cycle I treat slightly different. So instead of giving, it's a bit different, like elements, compounds, and then combustion products. This is a bit more confusing, so let's just take the above example, right? So I gave that's ethane, right? So what would be the elemental form of ethane? That would be, no, not 3C, it would be 2C plus that's 3H2, right? Would give you ethane, C2H6, right? Now if you combust both of them, the combustion products in the end will be the same, 2CO2 plus 3H2O, and you add plus O2 here, plus O2, because you're having to combust it, right? 3.5. So you can treat it the same way, add an H2 here, add an H1 here, and in this case it's an enthalpy change of reaction, which can also be the enthalpy change of formation, because you see that from the elemental stage you're converting it to a product. I hope that makes sense. So let's take another example and convert it into the cycle form, the combustion cycle form. Ethanol, not ethanol, sorry, propanol, CH3, CH2, CH2OH, propan1-ol plus O2 gives you carbon dioxide plus water, right? And there's 3 C's, 1, 2, 3, 3 C's, and 1, 2, 3, 4, 5, 6, 7, 8. 8 of 4, right? So 3 times 2, that's 6. 6 plus 10, so that's 5, right? To convert this to the cycle form, the combustion cycle form. Let's convert it. So this is, so first write the elemental form. So there's 3 C's, 3C plus 8H, not 8H, 4H2O, sorry, 4H2, which gives C2H5, CH2OH, right? And when you combust this with oxygen plus O2, there's 5 in each side, it gives you the same product, 3CO2 plus 4H2O, right? And this is the form, this is the cycle form. There's H2, H1, and delta HR or delta HF. So from this reaction you can find out delta HF, and you can also find out perhaps, well, I don't really know, whatever you could find out, right? And sometimes enthalpy change of combustion questions can be merged with the enthalpy change of formation, because you can calculate the enthalpy changes of formation, as you can see here, and also with the next part, something that we'll be talking about in the next part, which is, if I recall correctly, it's something regarding measuring enthalpy changes with Q is equal to mc delta T, right? Enthalpy change of water. But let's not worry about that for now. I hope that makes sense. So now let's move on to a few past paper examples. So here I have two past paper examples of what we've covered in this lesson, right? I'll just solve it on the screen. Unlike enthalpy changes of formation, enthalpy change of combustion questions are not as common, and whatever, like the two questions we'll be solving right now, like here, is pretty much the way they ask enthalpy change of formation questions and questions involving enthalpy changes. We won't be covering bond energies in this part, we'll be covering it in the next part, so that is also another thing that they can involve, but this is the most common one, okay? These type of questions are most common. So let's go on to solve. So magnesium peroxide is made in the following reaction, and they've given you the enthalpy change of reaction for this reaction. So we just treat that as delta HR. So the first question is the peroxide ion O2 minus. Deduce the average oxidation number of oxygen in peroxide ion. Now this is not something from this lesson, but it's something from the redox of equilibria. So you see that there's two oxygen atoms, so 2x is equal to minus 2, right? So x is equal to minus 1. Therefore the average oxidation number is minus 1. Now this is what we just talked about. Define the term enthalpy change of formation, not standard enthalpy change, just enthalpy change of formation. So that is enthalpy change when 1 mole of a compound is formed from its elements in standard states. Pardon the bad handwriting. Let's move on to the next part. Use the data given to calculate the enthalpy change of formation of MgO2. So you look back at the data and you see that they've provided you with standard enthalpy change of formation data, and which is like a very big giveaway of what type of cycle that you must use, which is the enthalpy change of formation cycle. Now recap that the enthalpy change of formation cycle is reactants to give products, right? And from their elements. So let's just erase this, yeah. And let's write the actual reaction down here. Just give me a minute. So the reaction is MgO. Okay, so the actual reaction is MgO plus H2O2 gives MgO2 plus H2O, right? And let's write their elemental forms. So Mg plus O2, right, plus H2. Now they don't usually give marks for drawing the cycle, so you don't really have to balance the elemental part out, but sometimes they do give marks for the cycle. That's when you do have to balance the elemental parts out. So in this case they're not giving marks for the cycle, so I will just leave the elemental parts as it is. So this is H2, this is H1, and this is delta HR, right? So delta HR is 96, and what are we supposed to find? MgO2. MgO2 is on the H2 side, so H2 is equal to H1 plus delta HR. So first find out what is H2. So H2 is H1. What is H1? H1 is the enthalpy change of formation plus the enthalpy change of formation of MgO and H2O2. MgO, and so negative 602, negative 602, minus 188, right? 188 plus minus the HR. What the HR is 96. So when you put this in the calculator, you get the answer as minus 886, right? kJ mole minus 1. And H2 is composed of the enthalpy change of formation of MgO2 and H2O, right? So you make that as X plus minus, I believe it's minus 286. 286 is equal to 886, right? Therefore, x is, so when, wait, minus 886, yeah. So when you move this to this side, minus 886 plus 286 will give you minus 600 kJ mole minus 1. Simple, right? You have to write the sign. It is very important. Okay. In the next part, magnesium peroxide decomposes slowly to form magnesium oxide and oxygen. Use your answer in G1 and the data in the table to calculate the enthalpy change of this reaction. So enthalpy change. So we've calculated mainly with formation values. So we'll also use a formation cycle here. So MgO2 gives MgO plus half O2, right? And the elemental forms Mg plus O2. No marks given for cycles, so I'll just leave it on balance, H2, H1, delta HR, right? So in this case, we're finding out the enthalpy change of this reaction. So this reaction is delta HR, so when you make delta HR the subject, it'll be H2 minus H1. So H2 is the enthalpy change of formation of MgO, right? So which is minus 602, I believe, minus this in brackets of oh yeah, and I'm not including this because it is an element alone, so it does not have an enthalpy change of formation value. And H1 is what you calculated up here, the enthalpy change of formation of MgO2, which is minus 600. So minus 602 minus minus, so that becomes plus, equals minus 2 kJ mole minus 1. Pretty simple, right? Let's move on to another example. So this is an example directly. So nitric acid can be made by reacting nitrogen dioxide with water. The enthalpy change of this reaction can be measured indirectly using a Hess cycle. So you can treat it as an isolated system. Explain what is meant by the term enthalpy change of formation. See, standard is not mentioned. Sorry, standard is not mentioned. So you just give the definition of enthalpy change of formation, which is delta HF. We talked about this previously, so I won't be answering this question in this paper. Complete the Hess cycle. Complete the Hess cycle using the given values in the table and hence calculate the enthalpy change of this reaction, right? So in this question, I believe it's 3 marks. Yeah, so 3 marks. I'm assuming they're giving 1 mark for correctly labeling the cycle, right? So this cycle, you will get marks for. So you have to balance the elemental side. So you see that there is a nitrogen, right? So N2 plus O2 plus H2, right? So there's how many nitrogens are there? There's 3 nitrogens, right? So there's 6 nitrogens, so 3. And there's 7 oxygens, so that'll be 3.5. And there's how many hydrogens? 1, 2, 1, 2 on both sides. So we'll just leave it as 1. Okay. Well, because you're leaving it as 1, you don't really have to write it, so just ignore that. And then you form the formation cycle, H2, H1. And what are you being asked to calculate? The enthalpy change of reaction, right? So they legit just stated it for you that this is the enthalpy change of reaction. So H2 is equal to H1 plus delta HR, therefore delta HR is equal to H2 minus H1, right? Delta HR would therefore be H2, what is H2? Twice into enthalpy and HNO3, so minus 173. Oh yeah, and realize I'm doing 2 into because in the table it's only for 1 moles, but over here there's 2 moles present, so I'm multiplying it with 2. And plus NO, and NO is 91.1. 91.1. Wait, just let me rewrite that clearly. 91.1, right? Minus of H1. So 3 moles of NO2, that is 3 into 34. 3 into 34, and H2O plus H2O minus 286, right? I believe, yeah. So it should turn out to be minus 70.9 kJ mole minus 1. Minus 70.9. Again, the sign is very important when it comes to enthalpy changes. This part is not from enthalpy changes, yeah. So but you can still attempt it if you want to. Feel free to pause the video and attempt it yourself. Nitrogen, oxygen do not react at normal atmospheric temperatures. You have to mention the triple bond of nitrogen and its inert characteristic, and how the triple bond has a high bond energy value. State one way that nitrogen oxides are produced naturally. That's lightning. Explain why it is described as a homogeneous catalyst. So that is from reaction kinetics lesson, right? If you haven't checked it out, I suggest you do so to be able to answer questions like this. But basically, it is because homogeneous because it is in the same phase, catalyst because, well, it reduces the activation energy by providing alternate pathway, thus increasing the rate of reaction, right? And write equations which describe the two reactions when NO2 acts as a catalyst. So that is a part of reaction kinetics and also part of organic. So I won't be doing that for now. Anyway, those are the two examples, the two example questions for enthalpy change of formation. That's really it for this part, the first part of this lesson, right? Because I haven't covered any enthalpy change of combustion, I'll just give a brief example, like a brief example question. There aren't many, but anyway, I'll just give a brief example question. So, sucrose, okay? Sucrose, complete combustion. And the molecular formula for sucrose is C12H22O11. For those of you taking bio, this compound is pretty familiar, right? So complete combustion of sucrose, and the enthalpy change of combustion, standard enthalpy change of combustion of carbon is minus 394, and standard enthalpy change of combustion of H2, sorry, H2 is minus 286, and standard enthalpy change of combustion of sucrose is minus 5640, all units in kg mole minus 1. So find out the standard enthalpy change of formation of sucrose. Feel free to pause the video and give it an attempt yourself. Anyway, let's continue. So sucrose being formed from its standard elements, because it's a combustion cycle, right? So sucrose being formed from its standard elements and both undergoing complete combustion. So sucrose being formed from its standard elements, so C12H22O11, right? From its standard elements, so that is 12C plus 11H2 plus 5.502, right? Yeah, 5.502, which completely combusts to give CO2 plus H2O. No marks are being awarded for this completely balanced, so I'll just leave it as it is. So H2, H1, and delta HR, and since it's from standard elements to a product, is also equal to the delta HF, right? So when you make delta HF the subject of the equation, which is H1 minus, I believe, yeah, so it'll be H1 minus H2, right? So H1 minus H2, and so delta HF, or delta HR, delta HF should be, let me just do it in the calculator, minus 2234 kg mole minus 1, which is also equal to delta HR. So that is pretty much it for this part of the lesson. In the next part, we'll be covering the basic definitions of different enthalpy changes. I hope you understood. If you haven't, please leave a comment in the comment section below. If you have understood, or if you helped you in any way, feel free to like the video and subscribe.